Hello, my name is Andy Benson, and I worked with Patrick Flynn to create a smart hardware fuzzer based on AFL++ and the symbolic executor provided by SimCC. All right, to understand our project on hardware fuzzing, we first have to cover what is fuzzing, what is symbolic execution, and finally, what exactly is hardware fuzzing. Software fuzzing is a testing technique to find bugs and vulnerabilities in programs. It works by repeatedly mutating inputs to find bugs. In the above diagram, the random inputs are presented in binary, but this can range from anything from structured to unstructured inputs of different kinds depending on the software being tested. The software being tested can range from simple programs to entire libraries, such as those tested by libfuzzer. This paper focused specifically on coverage-guided fuzzers, such as AFL. These record when inputs hit new untouched parts of the program and record these seeds as interesting and add them back to the seed pool for further mutations. The software can also record crashes to determine what inputs broke the program during execution. AFL is a popular fuzzer, which is shown in the image on the right. It uses coverage-guided fuzzing to find bugs and crashes. To produce new inputs, it uses a variety of bit and byte flips, trimming, arithmetic operations, and etc. Fuzzing is an effective tactic for discovering bugs due to its unstructured nature. It has the ability to catch bugs that would have been missed by normal user testing, and it can be left alone for long periods of time. This makes it an ideal tool for attackers to passively probe different programs for vulnerabilities. Some drawbacks of fuzzers are that they struggle to explore new edges once they get stuck. This is because the random inputs might go down certain branches and never hit all the edges. This is especially true when the seed pools become so massive that it would take too long to process and mutate on all the interesting seed inputs within the designated time frame. Additionally, some fuzzers need very complicated harnesses to provide inputs into certain programs. Finally, fuzzers normally have to run for a very long time on large open source programs to actually find bugs. To address the problems of fuzzers getting stuck, we use symbolic execution. Symbolic executors are the second piece of our solution. Symbolic executors normally work by translating the program into an intermediate representation, which in our case would be LLVM bitcode, which is executed symbolically. This means that an SMT or SAT solver is used to find given specific values of all the variables should the conditions be satisfied as true. For those who do not know, SMT or satisfiability modulo theories is a generalization of SAT, which is a Boolean satisfiability problem. These problems boil down to a series of complex Boolean operations, which tries to find any combination of true and false values of variables that can evaluate the solution to be either true or false. This is very helpful to solve complex sequences which could easily be missed by random mutations used in fuzzing. SMT solvers implement these theories to try and solve SMT problems based on a subset of inputs. When solving these expressions, some constraints can be too difficult to solve or unable to be determined. SMT problems are also inherently NP hard. SMT solvers were originally too computationally intensive to be used efficiently to solve problems, but by the 2000s, computational power had increased to the point where they became useful. One common symbolic executor is Z3. Concolic execution is a hybrid method of using both symbolic execution and concrete execution to solve for specific constrained conditions. Symbolic execution, as mentioned before, is just solving problems with symbolized inputs, while concrete execution is testing with specific real inputs. Concolic execution provides much greater flexibility to solve conditions compared to using symbolic execution alone. For example, say that a given path is infeasible to solve with an SMT. In order to still get potential outputs that might satisfy this conditional, we can substitute actual values into the program that allow the program to run. This relaxing of conditions has allowed concolic executors to take on much more than pure SMT solvers. For an example of how this works, consider the example on the right. To examine the BAC function with purely symbolic execution, we get the condition x is not equal to y times y modulo 50. This is a very difficult statement to solve given that modulo operators are hard to solve in an algebraic sense. With concolic execution, we can instead treat foo as a concrete block where we do not solve for its contents, but instead use it as a variable itself. The function f of y is not equal to x. It's far simpler to solve. Basically, the combination of concrete and symbolic allows for easier computation of complex paths that might beset the SMT solver. These concolic executors can be paired with fuzzers to provide the concrete inputs that can be used along with the symbolic inputs from the SMT solvers. So what is hardware fuzzing? Hardware fuzzing is a field of study which attempts to use fuzzers to provide inputs into hardware models in order to cover all the different possible states of a CPU or a peripheral device. In this project, we focus on testing a processor core as well as a sample program that we call the sample log. Hardware fuzzing is one method for hardware verification, along with a formal verification, such as assertion proving, or dynamic verification, such as the simulation-based random regression. Hardware fuzzing offers a more efficient approach to full formal verification, as well as more guidance that the random regression, which struggles as the device under test increases in complexity. Generally speaking, most hardware fuzzers work by taking the designs written in an HDL such as Verilog or a higher level HDL such as Chisel and simulate them. These simulations can be done in Synopsys VCS, Siemens ModelSim, or in our case with Verilator. Verilator is an open source software tool that can be used to convert Verilog to C++. Once the hardware design is in C++, either a traditional software fuzzer like AFL++ can be used, or a hand-created fuzzer can be used to provide inputs into a test harness that simulates the core. This is the general approach of our solution with smart hardware fuzzing. The largest difference between hardware fuzzers and software fuzzers is the way in which bugs are detected. Hardware does not have a traditional definition of bugs like software, since hardware will not crash. Instead, hardware will enter into incorrect states. For example, the Spectre and Meltdown attacks were hardware faults that allowed users to break the confidentiality, integrity, and accessibility privileges of the software running on the hardware. This is why hardware bugs and exploits are so damaging, since all the software running on top of this hardware is now at risk. When implementing hardware fuzzers or quote-unquote bug finding, hardware fuzzers will use different differential fuzzers or handcraft checks to make sure that the hardware does not enter into an invalid state. Differential fuzzers work by comparing the outputs of the device under test to a given input compared to the golden reference model to see if differences arise in the states, such as the register values that can get set. These can alert the user to potential problems with the core. In contrast to differential fuzzing, assertion checking uses handcrafted asserts that trigger crashes in the code when an incorrect state is hit. This is basically making the hardware bug into an actual software crash. Both of these approaches are quite intensive as they necessitate either inserting crashes with the insertions or possessing a golden reference model. For that reason, our paper focuses on how to better explore the device under test, because once we have maximized the coverage, because advances in coverage would be applicable to any device under test produced, whereas our assertion and reference model checking would be limited only to cores we tested. We therefore believed our time would be better spent maximizing our coverage. Past efforts in software fuzzing have included such papers as RFuzz or fuzzing hardware-like software. RFuzz was one of the first efforts in the field which converted hardware designs into software and used a re-implementation of the software fuzzer AFL to provide inputs to the device under test. The hardware designs for RFuzz were in FIRRTL. To guide its mutations, RFuzz made use of MUX coverage to identify if a new multiplier was hit or not. For those unaware, a multiplexer is simply a piece of circuitry that selects a single output signal from a given input selection of input signals. In RFuzz, seed inputs are considered interesting if they hit new multiplexers, so these seeds will get further mutated. As this is a re-implementation of AFL, it is not as efficient as modern software fuzzers such as AFL++, which provide far better performance. This is what fuzzing hardware-like software used in its implementation. Since software fuzzers are so much more mature than anything that can be created just for a single hardware fuzzing paper, fuzzing hardware-like software used AFL++ along with a harness to provide all the core inputs into different processors. These approaches have been incredibly effective at exploring hardware designs, but they still fall short of the 90% plus goals used for software coverage. This is because hardware designs are just too complex for random guessing to hit all the edges, especially in a short period of time, such as 24 hours. As shown in the image in the bottom right, variated code does not structure itself in a way where random inputs can easily hit all the different branches. It is not written as a normal programmer would construct the code. This is where we present using concolic execution. For specific blocks of if statements which are hard to solve for, concolic execution might provide an alternative approach to provide input cases to hit these hard-to-reach places. In this paper, we will further explore this by using both a sample lock and a RISC-V core as our test devices.
In this section, we will discuss the tools, compilers, and fuzzers used to create the hybrid fuzzer, which we call a quote-unquote smart hardware fuzzer. So for our project, it can be simply stated as a combination of a concolic executor and an advanced software fuzzer that we use for hardware designs. For our software fuzzer, we used AFL++. As mentioned earlier, it is one of the most advanced open source fuzzers available on the market. As for our concolic executor, we use SimCC. SimCC is an open source project that completes concolic execution with the assistance of compilation instead of interpretation. This difference allows it to perform much more efficiently compared to previous concolic executors. The idea is not novel in and of itself. A similar undertaking has been done by the paper Hi-P-Fuzz. That paper used a hand-spun fuzzer and symbolic executor to fuzz processor core designs. This paper was a good proof of concept, but it lacks any form of GitHub repository or public tools for future development. By using a closed source model for their project and handwriting all of their code, this limited the overall capability of their fuzzer. By using the most advanced open source options available, we hope to build a tool that can aid all hardware verifiers while still being relatively easy to set up without much time needed. The reason why this strategy is effective is because the concolic executor SimCC uses to find new inputs is directly fed from the output seeds of AFL++. So for each new seed added to the queue, it will attempt to solve different constraints to try and break through to new edges in the design that the fuzzer might struggle to hit. So for this project, we use the software fuzzer AFL++. AFL++ operates similar to other coverage-guided fuzzers by instrumenting the source code and checking to see when specific inputs hit different code edges. These inputs can be marked as interesting if the edge has not been touched previously. For our mutation strategy, there were two avenues we could have gone down: a custom mutator that provided only valid RISC-V instructions, or random inputs. Due to the fact that we were testing on the sample lock and a simple RISC-V core, we opted to use random inputs. This is also due to the fact that random mutation is faster than custom mutation, since the random mutation mostly uses bit and byte flips with simple arithmetic. These are much more efficient than the custom mutator, which would have had to hand assign each part of an instruction based on its RISC-V type. Another counterpoint against the custom mutator is that the possible instruction space for RISC-V within a 32-bit instruction is so large that random is not actually that inefficient. Given a sufficiently powerful computer and a long enough run, a random mutator should save enough valid instructions to explore as much as the custom mutator. Due to the brevity of this project, we did not confirm these suspicions, but initial testing showed that random results and custom mutator results were not significantly different in edge coverage. Another reason why we used AFL++ is that it has some integration already with SimCC. AFL++ can be used with both a master session and a secondary session. The master session uses deterministic changes to try and find new inputs, while the secondary session uses completely random mutation to find new inputs. This approach is generally better at increasing coverage faster. SimCC's concolic executor can interact with these interesting seeds, as explained on the next slide. So SimCC is actually a compiler that instruments the codebase with calls to a runtime library, which runs concolic execution to solve constraints within the code. Taking regular program inputs as seeds, it works to solve conditions using either Z3, which is an SMT solver, or QSYM, which is a more advanced symbolic executor that selectively switches between concrete and symbolic execution to provide the user with more inputs to harder to reach branches. SimCC was so influential when it was released because traditional symbolic executors had to interpret each line of code as it was run. This created massive overhead since every instruction had to be processed symbolically in real time. By using a compiler, this overhead only has to be handled once. When inputs hit the instrumented branches, the solver can then be called as needed, reducing unnecessary computations. SimCC solver operates at the IR, or intermediate representation level, of LLVM. IR is what the compiler converts all the C++ code to before it becomes machine code. This choice is made not only to avoid tying SimCC to a specific programming language, but also to make it easier to implement a compiler path for. When the IR is processed, the runtime library handles all symbolic execution. For example, when the program checks if two variables are equal, this can be expressed as a symbolic execution, or a symbolic expression. A call to the runtime library is inserted to obtain that symbolic expression and associate it with the resulting variable. By instrumenting once at compile time, different inputs can be run without needing to re-instrument the code. These symbolic expressions are stored in shadow memory, with fixed offsets used to access different areas, similar to how LLVM's other sanitizers work. Shadow memory allows efficient tracking of symbolic values without modifying the actual program state, which keeps execution performance high. For SimCC, any code that is not instrumented is automatically treated as concrete input. This allows SimCC to work efficiently with large code bases, as only the critical parts need to be symbolically executed while the rest runs normally. So our first test subject was a sample lock. This was taken from the paper Fuzzing Hardware Like Software, as the sample lock represented a proof of concept to evaluate hardware fuzzing. The locks themselves operate similarly to physical locks, in that you input a combination in hopes of gaining entry. Our sample lock takes an input code of 8 bits and a 2-byte state code, along with clock and reset signals. As the fuzzer explores new areas within the code, it saves those inputs as interesting. Therefore, as it begins to work through the lock mechanisms and hits new checks, it saves those inputs as interesting. At least, that is how the fuzzer operates. The concolic executor, on the other hand, will go and solve the constraints of the lock and generate the final key to unlock it. This piece of hardware is mostly used as a proof of concept, as it is far simpler than a traditional processor core. BioRISC, on the other hand, is a full RISC-V core written in Verilog. It implements the 32-bit ISA with integer, multiplication, division, and CSR extensions. It has a superscalar pipeline that processes 2 instructions per cycle and makes use of a 6-stage pipeline. It is meant for deployment on FPGAs and can boot Linux, and it has 978 stars on GitHub. This is a very popular core in the RISC-V community, especially for hobby and research work. Now we shall show a quick demonstration of the concolic executor running and using AFL++ also. So this screen here is showing the symbolic executor running. So basically, this is SimCC. It goes through and it symbolizes all of the different functions within the code. And so all of these are our variated functions here in Byrisk. And then it will go through and try and find interesting inputs to explore new areas within the code base based on our seed input. So I just gave it a very simple blank seed input, and it gave us these 8 different alpha cases that would be interesting to look at. And so when you combine this with AFL++, it's basically anytime AFL++ finds a new edge, SimCC will try and go and find new interesting edges based on these new seeds too. So it's basically building off of the progress that AFL++ makes, and then also it updates AFL++ of any progress that it makes. And then this is the statement from AFL++. So basically we were running a timeout for 24 hours, calling our AFL fuzz. We set our G values to basically say, make sure that we get 2,225 bytes as input so that we have a sufficient amount of input based on the number of cycles we're running our simulation for. Go and take the input from the Byrisk seed folder, output it to results test, and then run our Byrisk AFL executable. So then you can run this and see that it goes through, and it doesn't find a whole lot of coverage initially. It only sits around 31%, but that's because we gave it a blank input seed, and so it takes a little bit of time for the random mutator to actually start discovering interesting edges. But in the end, it hits about 80% coverage for AFL++. And so this is just the general approach to the problem. So now that the demonstration is over, we can go over the results of our project.
To test our SimCC setup with the sample log, we ran a plain fuzzing session aiding concolic execution. The concolic executor effectively decoded the logs, but the fuzzer was not as effective at finding coverage. This is due to the fact that fuzzers struggle to generate random inputs to break into long sequences, such as logs. The concolic executor, on the other hand, was able to easily symbolize the sample lock and provide new edges. The sample lock was so simple that the concolic execution was not really needed. This was given as an example to show that the symbolic fuzzer could be used with Verilator, AFL++, and SimCC, which it is. Some minor problems along the way include getting the correct versions of Verilator, AFL++, and SimCC that were compatible, as SimCC is unable to function well with threaded applications. So we had to make sure that the Verilated programs we created would follow these directives. For our sample lock results with SimCC, we got 75 of 123 edges covered in the code. This is 60.98%. This does not sound very good, but it is because we do not limit our search space with an allow list, so we are counting all the possible functions for our edge calculations. Our fuzzing setup was still able to unlock the lock, which was the main goal of this test. The sample lock solution was actually found through the fuzzer, which SimCC provided some other seed inputs that explored new branches in the code, but it was not the source of the lock solution. In comparison with the sample lock, Byrisk is an actual RISC-V core. To test it with the concolic executor and fuzzer, we provided random inputs directly to the core module. We cannot use the regular memory model, as SimCC cannot trace the inputs from the input file to the buffer through the redirection needed to place the inputs into the memory model. We took our design inspiration from the fuzzing hardware like software paper, which also featured the sample lock. This interface is fine, but serious improvements could be made to eliminate the many wasted inputs it creates that do not set the valid bits when passing in data. Byrisk was compiled with 2 different versions of Verilator, one for the AFL++ executable and one for the SimCC executable. This was due to complications with threading. Samplelog was able to compile both executables with Verilator 4.2, while we had to use Verilator 5.016 and Verilator 5.002 for ByRisk. To test ByRisk, we also ran two separate trials, one with just the AFL master and AFL secondary runs, and another with AFL master and AFL++ secondary and the SimCC concolic executor. The SimCC concolic executor found edges initially, but as the fuzzers explored deeper and deeper into the core, SimCC struggled to produce new, unique inputs. This is unsurprising given the limitations of the engine, especially with the 10-second execution limit for the SMT. Overall, we found 1.89% coverage improvement with SimCC between the two approaches. This is around 80% of total coverage of the program. To get better statistical significance, we would need to run more trials if we had a larger time frame. These results generally show that the current state of these results generally show that the current state-of-the-art symbolic executors can be applied to hardware designs, but their computational limitations are such that fuzzers are still able to better produce coverage. These processors are also not meant to be designed as a log, so incremental changes to inputs should be able to find new edges within the design. Our contributions in this paper show that concolic execution is possible on hardware given open source tools, and future advances might help generate coverage and create synergies between the tools.
All right, and just on to our final conclusions and future work. So, as our results have shown, the current implementation of SimCC with our fuzzer is not that effective compared to just running the fuzzer at full capacity. To improve the implementation of SimCC, we have several ideas. The first and most straightforward would be to increase the timeouts used by the program. There are several places that set timeouts, and these need to be adjusted across the board. The first set of timeouts to change are in the concolic executor of SimCC. This is set to 30 seconds, which is not bad, but testing with adjustment should be done to determine the best value based on the complexity of the design we are testing. The second timeout that needs to be tested is actually within the QSYM implementation that is used to power the backend for symbolic execution. The QYSM timeout is set to 10 seconds, which can be very restrictive, especially considering we're using large variated programs with sometimes hundreds of nested if statements. These would take a long time to calculate, especially when the inputs are far from the expected point of execution. Some challenges with this approach will be to determine the best testing strategy and usage strategy. Previous hardware fuzzers, such as HiPFuzz, created their own scheduling algorithm to alternate between the symbolic executor and the fuzzer. This assumes that it is worthwhile to switch between the two on a consistent basis. This is questionable considering the fuzzer used in the experiments was handmade and likely featured fewer optimizations than AFL++. I believe a better approach would be to use AFL++ initially to generate a large overall coverage during the 24-hour testing. After the fuzzer has not found any edges for a sufficient period of time, the symbolic executor needs to be allowed to run for a sufficiently long period of time to determine new edges. Given the previous problems with timeouts, I do not want to cut the symbolic executor off before it would have enough time to solve a hard formula. These tests will also be important since we normally test fuzzers on a single core for 24 hours. The balance between the fuzzer and the symbolic executor will likely vary depending on the processor core complexity. Additionally, more trials could be run in the future because we only had time to run one for each of our test cases for 24 hours. Overall, further testing needs to be done to better perfect the symbolic executor. Both changes in the timeout and scheduling could potentially help further fuzzing performance on these cores. It is still necessary to determine if symbolic fuzzers are actually worthwhile or if increasing the efficiency, mutation, and seeding of the fuzzer is better, but that is a problem for another day. Thank you for listening to our presentation.